For the final video in this short series, I want to go back and look at a circuit that we first came across when we started studying time-variant circuits. This one. You may remember that at the time I said that I wouldn't bother to solve this differential equation because I would be introducing a technique later on which allowed you to work out the voltage across the capacitor without having to do any calculus. That time has now come. We can use this technique of phasors to solve this circuit. The analysis looks like this. First of all, we take the voltage source and we express it in terms of a phasor. Well, the phasor that represents V0 sine omega t is V0 over j, or just minus j times V0. It has to have a phase angle of minus 90 degrees. It starts there, so that when time starts to increase and the calcisoid being represented by this phasor is going round in this direction, the real part of this cissoid will start at 0 and start to move positive before going back again. On a time plot, that would start at 0. If this is amplitude volts and this is time, that means we'd be starting at 0, going positive up to V0 there. And then the real part would drop back down to 0 again as the cissoid ended up back at the positive imaginary axis. And then as the cissoid went to here, the real part would go down to minus V0, and as the cissoid completed an entire circuit, the real part would go back up to 0 again, and we would have a sine wave. But we have to start here at a negative imaginary point to get this sine wave behavior. So that is our phasor representation of our voltage source. We can then just apply the potential divider equation. The voltage across the capacitor as a phasor is equal to the voltage at the top of the potential divider here as a phasor. That's V0 over j, multiplied by the impedance of the capacitor, which is 1 over j omega c, divided by the total impedance in our network, which is R plus 1 over j omega c. Multiply top and bottom of this equation by j omega c, and we would just end up with V0 over j divided by 1 plus j omega c times R. To convert this back into the time domain, we'll need to work out what the magnitude and the phase of this is. So, noting that V0 over j is V0 with a phase angle of minus 90 degrees or minus pi over 2 radians, I could write that term as V0 times e to the power of minus j pi over 2. The term on the bottom, 1 plus j omega cr. Well, if I plot that on an Argand diagram, it would have a real part of 1 and an imaginary part of omega cr, where this distance here is omega cr. It would be there. So I can express this in terms of a polar representation by using good old Pythagoras to work out the distance from the origin, that's the amplitude of this phasor. So that would just be the square root of 1 plus omega squared c squared r squared. That's just Pythagoras in this right-angled triangle. And the phase angle would be that angle there. And that angle is tan to the minus 1 of omega cr divided by 1, which is just tan to the minus 1 of omega cr. That's the angle. So I could write this as e to the power of j tan to the power of minus 1 of omega cr. Now, that makes the amplitude of the voltage across the capacitor, V0 divided by square root of 1 plus omega squared c squared r squared. And the phase, well, I can use the property of exponents, that x to the power of a divided by x to the power of b is x to the power of a minus b, and just write this divided by this as e to the power of j minus pi over 2 minus tan to the power of minus 1 omega cr. That's the phasor representing the voltage across the capacitor. So I can convert that back into the real time domain waveform by multiplying by e to the power of j omega t and taking the real part. That would give me the voltage across the capacitor is V0 over square root of 1 plus omega squared c squared r squared times cosine of omega t minus pi over t minus tan to the power of minus 1 omega cr. And here is where I can use the useful result that cosine of theta minus pi over 2 is just equal to sine of theta, and therefore write this as V0 over the square root of 1 plus omega squared c squared r squared times sine of omega t minus tan to the power of minus 1 omega cr. And that's it. No calculus required. We just do the problem using phasors and the potential divider equation. And that brings us to the end of the AC analysis videos.